Hello and welcome to the BS Academy. So recently IIT Bombay has changed their syllabus a little bit to the each branches. So according to the new syllabus, we have made these charts in our best possible ways, and these charts basically give you an idea how to prepare your own charts, because ultimately you have to make your own charts of every subject, and after that you will get that confidence. So basically these charts will give you the ideas and perfect information after referring all the reference books.
Now in the third chart of the strength of materials will include the slope and deflection and the theory of pure bendings. Let's begin one by one. First one is slope and deflection. Before that, if you are new to our academy, then please subscribe for the coming videos and the links for the short notes which are in description box. Here you can see that the definition of deflection, it is the vertical displacement of any point from its initial position up to elastic curve, and delta max is less than delta allowable. It is the condition for design of a beam on the basis of stiffness criteria, and the shape of the elastic curve depends on the types of loading. Here note that if SF is equal to 0, then BM is equal to 0, and the diagram will be like straight line and linear curve. Then if SF is equal to 0, then BM will be constant, and the shape of the BM will be like arc of a circle. Then SF is not equal to 0 and BM is also not equal to 0, then the curve will be like parabola, and it will be of second, third or fourth or any order of degree. Then for the straight beam concept, here you can use the equation of delta C is equal to delta B plus BC into theta B. Then after standard formulas from which the questions were so many times asked in the GATE examination, here note that these formulas are valid for only the prismatic beams, and EI is equal to flexural rigidity or bending rigidity. Here for the first type, theta B is equal to ml upon EI and delta B is equal to ml square upon 2 into EI. Then in the second type, the load is acting at the end, theta B is equal to PL square upon 2 into EI and delta B is equal to PL cube upon 3 into EI. Then third one, UDL is there, then theta B is equal to WL cube upon 6 into EI, delta B is equal to WL raised to 4 upon 8 into EI. Then for UVL, delta B is equal to WL cube upon 24 into EI and delta B is equal to WL raised to 4 upon 30 into EI. Then for the fifth type, the load is acting at the center, theta A is equal to theta B is equal to PL square upon 16 into EI and delta C is equal to PL cube upon 48 EI. Then for the sixth type, theta A is equal to theta B is equal to WL cube upon 24 into EI and delta C is equal to 5 by 384 into WL raised to 4 upon EI. Then in the seventh type, here the moment will be acting from both the ends, theta A is equal to theta B is equal to ml upon 2 into EI. Then delta C is equal to ml square upon 8 into EI. And for the eighth type, UL at the center, delta C is equal to WL raised to 4 upon 120 EI. Then 10th one, delta C is equal to L square upon 8R, which is the equation for pure bending. Then there is the example, if two bars are connected face to face and rigidity will be 2EI and EI, then theta C is equal to 5 into PL square upon 60 EI and delta C is equal to 3PL cube upon 60 into EI. Then after superposition principle, for the first one, if the UDL and point load both are acting, then it will be near equal to the equations of UDL and point load. So you can say that delta B is equal to WL raised to 4 upon 8 EI plus PL cube upon 3 into EI. Similarly for the second one, here you can use the equation of delta B is equal to WL raised to 4 upon 8 into EI minus WL raised to 4 upon 30 into EI. Then for the third type, you can use the equation of delta A is equal to 5 upon 384 into WL raised to 4 upon EI and Maxwell's reciprocal theorem. The equations for the theorem is delta 1 upon P2 is equal to delta 2 by P1 and theta 1 upon M2 is equal to theta 2 by M1. Here note that only for concentrated point load and concentrated moments. Then there are some more examples for the values of delta B and delta C. There are methods of finding the deflection. First one is the double integration method or Macular's method. The equation for this method is m is equal to e into I into d square y upon dx square. So you can say that m is equal to e into I into y double dash. Here the final equation will be e into I into y is equal to mx square by 2 plus c1x plus c2. Then the second one is modified Macular method, in which the equation will be like e into I into y is equal to ra into x cube by 6 plus c1x plus c2 minus p1 into x minus a cube by 6 minus p2 into x cube by 6. Then the third method, area moment method, or you can say that the Morse method. It is used for both the prismatic and non-prismatic bar. In the first theorem, theta b minus theta a is equal to area of diagram m upon ei, and in the second theorem, theta b is equal to area of m upon ei into x bar. So you can find the values of theta b minus theta a by finding the area of m by ei, and for delta b you can find the area of m by ei into x bar. Then fourth one is strain energy method. For this method, the equation of delta, which is equal to integration m into x into del mx upon del p into dx divided by ei. Then theta is equal to integration mx into del mx by delta m into dx divided by ei. And here equation of u will be integration a to b mx square dx upon 2 into ei, which is the equation of strain energy. This method is also known as the Castigliano's method. Then fifth one is the conjugate method. This method is also used for both the type prismatic and non-prismatic bars. Here loading diagram is equal to m by ei diagram of the real beam. First we have to convert the real beam to the conjugate beam. For that, these are some rules for the conversion. You can take a screenshot. Then here SFD of the conjugate beam will be the slope diagram of the real beam, and BMD of the conjugate beam will be the deflection diagram of the real beam, which gives the value of delta B. So these methods you have to use only when the standard formulas you cannot use. Most of the time in the GATE examination, the questions were asked based on the standard formulas only. And sometimes you have to use the superposition principle and the Maxwell principle and the Maxwell's reciprocal theorem. Then after analysis of statically indeterminate beams, then first one is probe cantilever beam. For this type of beam, unknowns are 4 and equations are 3. So you can use the computability. Delta A is equal to 0 and theta is equal to 0 and delta B is equal to 0. Then for the fixed beam, 6 unknowns are there. And for the third type here, you can use the theta B minus theta A is equal to AS plus AF, and summation of AS plus AF will be 0. Then there are two special cases. For first one is the beam of uniform strength, and the second one is the slicing of beam. Here for the special case of beam of uniform strength, you can use the equation of Z is equal to BD square by 6 and sigma max is equal to 3 into px by BD square. In that also there are two cases are there. First one is
depth changing with the constant diameter, and for this type of case sigma max is equal to 3 into px by b into dx square. Then for second type of case b is not constant and d is constant, then sigma max is equal to 3 into px by bx into d square. The example is beam of uniform strength and a prismatic bar with the pure bending moment. Then for the second type of cases, then for the second special case, the slicing of beam. Here in that first case is horizontal slicing. Then the equation of z will be z solid is equal to b into nt square by 6, and z slice will be n into bt square by 6. Here n is equal to z solid by z slice. Second case is vertical slicing of beam. For this type of beam, for this case z solid is equal to nt into d square by 6, and z solid by z slice is equal to 1. Hence from long beams vertical slicing is more used in the practical cases. Then the next chapter is shear stress in beam. Here tau max always on neutral axis is not necessary. Then after material should be isotropic, homogeneous and should follow the Hooke's law. And third one is shear stress constant E2F and do not change with the width of the cross section B. Then changes along the depth. Here the value of shear stress at any level E2F is given by tau is equal to VA into y bar upon INA into B. Note that because of shear force V, the variation of shear stress is always parabolic along the depth with 0 at the top and bottom and maximum somewhere in the middle, here not necessary at the neutral axis. Then due to shear force V, shear stress will produce on two mutually perpendicular planes. First one is vertical plane parallel to the shear force. The second one is horizontal or longitudinal plane which is perpendicular to the shear force. Then third note is tau average is equal to V by B into D. Then these are some preferable areas which you have to take for the value of y bar. Like in the T shapes, you have to take the y bar from the bottom side, y bar is equal to d by 2. Then for triangle, y bar is equal to 2 by 3 into a from upward side, and for the circular, y bar is equal to 4r by 3 pi, which is for circle and semisphere. These are some values of y bar, which is the centroidal distance from the considered area from NA. Here one more note is there for the values of Z for the different shapes. First one is for rectangular cross section area, Z will be BD square by 6 if the cross section will be vertical, and for the horizontal Z will be BD square by, and for the horizontal Z will be DB square by 6. Then for the square, Z of square is greater than that of Z of diamond. Then Z of R is equal to a cube by 6, and here for Z of diamond is equal to a cube by 6 into root 2. And then after the fourth one is for triangle, Z is equal to BD square by 24. For hollow rectangle, Z is equal to BD cube minus BD cube by 60. And for solid circular, Z is equal to pi d cube by 32. Then for hollow circle, Z is equal to pi d cube by 32 into 1 minus k raised to 4. Here k is equal to di upon d naught, which is less than 1. Then the theory of pure bending, in that some assumptions are there. First one is material should be isotropic, then homogeneous and should follow the Hooke's law. Then Then there are four types of examples. First one is the strength comparison, and the second one is for the bending stress calculation. So for the first type of questions, you can use the relation of m proportional to z proportional to I by y, and for the second type of question, you can use the equation of m by I is equal to E by R is equal to sigma by y, then sigma max is equal to m by z. Then the third type, here it is the most useful equation, f is equal to sigma max upon y max into a into y bar. Then the fourth type of question, which is for the composite beam, m is equal to E strong by E weaker, then E steel by E wood is greater than 1. Then there are two special cases which we have discussed earlier. Then for the top and bottom fletching, the modular ratio will be sigma s upon Es and sigma w by Ew. Here S for the steel and W for the wood. Similarly, for the side fletch, sigma S is equal to m into sigma W. So this is all about the third chart of the strength of materials. Now in the fourth chart of the strength of materials will include the equations of shear stress in beam as well as the theory of pure torsion, and the next one is the complex stress and strain.